Hi, I'm Malcolm, an embedded software engineer here at SparkFun. Are you a programmer who wants to get started with embedded software engineering or interfacing with hardware and don't know where to start? Or are you a seasoned embedded systems engineer who wants to take your prototyping speed to the next level? Either way, you should consider exploring MicroPython. What is MicroPython? Let's get into it. To understand what MicroPython is, we first have to take a look at Python itself. Python is a dynamic programming language with very simple syntax that makes it fast and easy to develop with. Python is interpreted rather than compiled. Since computers only speak in ones and zeros, all programming languages need some layer to translate between the human-readable code that developers write and the ones and zeros, or object code, that the computer understands. For the languages that have traditionally been used for embedded development, like C and Rust, this is done via compilation. Large programs on our computers, like preprocessors, linkers, compilers, and assemblers, translate all the code from a program into ones and zeros at once, and then that is what we run on our computer or load onto an embedded device like a development board and run. Python, on the other hand, is interpreted. When you install Python on your computer, it installs the Python runtime that contains something called the PVM, or Python Virtual Machine. I'm oversimplifying a bit here, but essentially, Python translates and executes your code line by line into the ones and zeros that your computer understands. The key difference here is that instead of being converted into object code just once like a compiled program, Python is interpreted from source code into ones and zeros every single time it is run. This means that unlike C, where the compiler can exist on one computer and turn source code into object code that can be run on other computers or embedded environments, for Python, the PVM and runtime that's doing the translation and execution need to exist on the computer or embedded platform that is running the code. This is where MicroPython comes in. MicroPython is a subset of standard Python, or CPython, that's designed to run on an embedded environment like a microcontroller without an operating system. The standard Python runtime is very large. It has many built-in libraries and creature comforts that are part of what makes it so powerful and fast to develop, but that can also cause it to bloat to a size that is unacceptable for many embedded environments. MicroPython strips out many of the less necessary features of CPython, while also adding features that are more common to embedded development, such as interfacing with hardware pins, writing information over serial communication protocols, and configuring hardware interfaces, such as WLAN for Wi-Fi. There are different versions of this MicroPython firmware for different development boards. These implementations abstract away the complicated hardware differences between different platforms. This both makes it easier for developers to interface with hardware and also makes MicroPython cross-platform. It's able to run on many different hardware architectures without having to make many, if any, changes. Another benefit of Python is that since it can translate code into ones and zeros one line at a time, we can easily test individual lines of code. This is done via a REPL, or read, execute, print loop, which does exactly that. It reads a single line of code, executes it, and prints the results for us. When MicroPython is loaded onto an embedded platform, it outputs the REPL over one of its serial interfaces, like UART. We can then connect to it with our computer using a terminal emulator or the MicroPython remote control program, MP-Remote, and interact directly with the REPL on our board. We can use this to test lines of code, navigate the file system on our board, and execute entire scripts. This is especially useful for tuning hardware parameters. You can quickly, on the fly, tinker with settings, change values slightly, and play with the order of commands until you perfect your program, all without having to go through a lengthy compilation and loading process. Now, let's check out a quick example to see MicroPython in action. While MicroPython itself has abstracted away the details of hardware interfaces such as I2C, individual sensors and actuators still have their own sets of commands and protocols that they expect to receive over these hardware interfaces. Qwiic is just our little connector that makes it easy to use I2C without a bunch of sloppy jumper cables and soldering. One such Qwiic device is the Qwiic TMP117 high precision temperature sensor. Here I have the TMP117, an RP2350 IoT RedBoard flashed with MicroPython, a Qwiic connector, and a USB-C cable. When I connect the USB-C cable to my Windows computer, the board is enumerated as a COM port. And using the Thonny IDE, I can find my board, connect to it, and get access to the MicroPython read, execute, print loop. Right here, I can run individual lines of code directly on my embedded platform without having to create and compile a standalone program. In the book 1984, Winston Smith famously said, "Freedom is the freedom to say 2 + 2 = 4. If that is granted, all else will follow." Well, looks like we're already unlocking some freedom with MicroPython, because indeed typing 2 plus 2 into the REPL does print 4. And better yet, we didn't have to go through a compilation process to figure that out, or deal with any hardware setup to get it running on an embedded development board. Now, let's do something a bit more interesting. Let's connect the TMP117 to our board with the Qwiic Connect cable, and in the REPL, let's import the SparkFun Qwiic TMP117 Python module. Next, I'm going to create an instance of the Qwiic TMP117 class provided by this module, and finally, call the begin method of our class. Now, just like that, with a couple of lines of Python, we're ready to use our temperature sensor. For example, let's call myTMP117.readTempC, and voila, we're getting temperature values off of our device. Since MicroPython makes this initial stage of development so simple, you can focus your energy on making more complicated programs. For example, using the micro.web framework and MicroPython's built-in support for configuring a WLAN wireless interface, I was able to relatively quickly create a program to configure my RedBoard as a wireless access point acting as a web server to serve a little web application to display temperature from our TMP117. So now, in Thonny, we can see that I have the source code for my web app already on the file system of my board. All I have to do is click Run, and we see that the TMP117 gets configured, the WLAN interface gets configured, and that the server is serving a web page to this IP and port. Next, let's connect to the wireless network of my board, which is named IoT RedBoard TMP117 and has this password. And now we can see that it looks like I'm just connected to a standard Wi-Fi network, besides the fact that we don't have internet. On our client device, in this case my laptop, in a browser, let's visit the IP and port, and we can see this nice little thermometer application. It is displaying the temperature on the thermometer and allows the user to set high and low limits. It displays a red LED if the temperature goes above the high limit or below the low limit. This is a simple sensor, and thus a relatively simple web page, but you can imagine how, with a bit of tweaks, you could edit this web page to interface with a different one of our Qwiic sensors and display a different set of indicators and controls. I hope that this has been a useful introduction to MicroPython, that you found our little web app fun, and that you're already thinking of ways that you could use MicroPython to take your prototyping to the next level. You'll find links to the source code for our example, a list of Qwiic devices with MicroPython drivers, and a link to the SparkFun IoT RedBoard RP2350 with MicroPython below. As always, Viva la open source, stay safe, be kind, and happy hacking. I'm Malcolm. I hope you found this, as soon as it's rolling, I'm down. TMP117 high precision temperature sensor. Precision. TMP117 high precision temperature sensor. Dang, I cannot.